So do you remember this experiment which we had discussed previously?
So I guess we haven't discussed it.
We haven't?
We haven't discussed it.
Okay,
No.
alright. So up to this point, yeah.
Yeah, we know a bit, like after this point, the track, the bit will be in a turbulent flow, and at the end, there will be a reverse line again, right?
That's exactly right. Yes. So at up till transition point, here we have the laminar flow in place, and therefore you can see the thread is going to stick finely with the aerofoil or the wing, and post the transition point, the flow becomes more turbulent, and for that reason you can see all these zigzags coming up on the thread. And after a certain point, which we defined here as the separation point, yeah. The separation point, what happens? The thread is now facing air that is coming from underneath the wing. Right? Yes. Remember, and if you remember the discussion which we had earlier about induced drag, the air that is coming above is kind of pushed towards the wing root as well. So basically you have air coming in the opposite direction. And what does that do to the thread? It kind of lifts up and kind of goes disordered. So now there is no more attachment with the wing. The thread is going to kind of detach from the wing. Right? This kind of tells us where the transition point is and where the separation point is.
Okay.
Did you understand? This experiment kind of demonstrates transition point and separation point. Now think about it. What happens when you increase your angle of attack? What happens to the ability of... Okay, now what is the whole problem with this separation point? So transition point is still fine, because even after transition point, the airflow, even though it is turbulent, is still attached to the surface of the wing. But what happens after the separation point? It completely detaches away from the aerofoil. So now you can see that there is no big effect of so much of an area being there on the wing. It is not contributing to any form of lift.
Yes.
It is just simply equivalent to so much of a portion not being there on the wing on the first place. Not just that it is not producing the lift, it is also producing drag. Now it is just a surface hanging up there which is not producing lift but producing drag. What kind of drag is that? Just because there's a surface introduced to the airflow, it's a parasitic drag. Right? So there is one drag producing surface which is contributing very less or zero to the lift production. So ideally speaking, where would you want the separation point to be? More closer to trailing edge or more closer to the leading edge?
More closer to the trailing.
More closer to the trailing edge, right? The closer the separation point is to the trailing edge, the more wing area is what you're using for lift production. Right? On the other hand, if the separation point was far towards the forward edge, you can see so much of an area. Larger area is now not producing lift but simply acting as a drag producing device. Right? Do you understand? So the ideal position of separation point or even transition point on that matter is actually away from the forward edge, more towards the trailing edge. Right? Now can you tell me, so any kind of maneuver, any kind of design that is promoting these points, transition and separation points, to kind of move towards the trailing edge is not practically advisable. Right? So can you tell me a maneuver which can actually move these separation points? Sorry, what I said is wrong. Any kind of maneuver or design that is kind of moving the transition point or separation point towards the forward edge, the leading edge, is not advisable. Right? So you see here, can you tell me a maneuver which can actually shift these points towards the leading edge? Yeah. Pitch up, that's correct. So what happens when you pitch up?
Sir, intersect is down, is it?
pitch up. So what happens when we pitch up? What are we doing? This is the relative airflow. This is the code. What is this angle called?
Angle of attack.
Angle of attack between the relative airflow and the code is what is called as the angle of attack. What happens when you pitch up? How do you pitch up? What control surface is responsible for pitching up? Elevators, yes. Control column or the side stick. You push it towards you. The elevators kind of move up and you pitch up, right? What is happening when you pitch up? The aerofoil which was in this configuration, you have now pitched it up. The airflow is still coming from the same direction because you are still moving straight and level flight. Therefore, the airflow is still coming from the same direction, opposite to movement of the center of gravity of the aircraft. And therefore, what happened to the angle of attack? Angle of attack increase. So basically, as the angle of attack increases, now what happens to the area of lower cross section as the angle of attack increases? We have seen all these diagrams before. It reduces, correct? Let me just okay, I'll just probably draw it over here. So when you have a wing of so much this configuration like this, relative airflow, chord line, and this is the angle of attack. We're repeating this multiple times so that it will help you keep that more in your brain. So make sure you attend it. We have a boundary layer here. We have a boundary layer underneath also. We are more concerned about the boundary layer which is above. Right? Where is the point of least area cross section? That is here. Now what happens, as you said, you pitch up, what happens when you increase the angle of attack? We are increasing the angle of attack by pitching up, by using your elevators. Your airflow is still coming from the same direction opposite to the movement of CG, and therefore you can see that the angle of attack increases. Right? Now the boundary layer is again on the same thickness. So I'm just doing the same thickness straight here down. Right? This is the boundary layer. Now you see what happened to the point, where is the area of, where is the point of least area cross section? That is now here. And the corresponding point on the chord line is there. Right?
Okay.
So you see what happened to the, so what point is this? This point corresponds to transition point, right? But this is your transition point. So what happened to transition point here? So you can see transition point which was initially in this line, so much of a chord line. It was initially here. What happened to transition point? As you pitch up, your transition point is moving closer to the leading edge. As the transition point moves closer to the leading edge, what happens to separation point? That is also going to move closer to the leading edge because it follows the other, right? So if the separation point, say for example, was here, I'm going to SP for separation point. The separation point here will be moving more towards the leading edge.
Yes.
Thereby, what we explained earlier happens. Now you can see that so much of a wing area was useless in the first case. When you pitched up, now so much of a wing surface area is useless. It is not that it is not just producing lift, it is also acting as a larger drag producing surface, and you need more thrust now to actually overcome the drag. More fuel and less efficient. Right? Now what happens if you pitch this even forward? So you see the lift contributing surface here. Let's see that part. The lift contributing surface is only so much. In the first case, probably I'll take up to the separation point. So much is there. The second case, it is only so much. Is the lift producing surface, right? But this is the lift producing surface. Now will you understand if I draw the lift vector with maximum magnitude here and magnitude less on both sides, because the static pressure is least here and therefore the maximum lift force is going to be in the center and it's going to reduce. And we assume a point on the chord line from where the entire lift is assumed to act. That is what is called a center of pressure. Actually it is distributed throughout the wing. It's a point of assumption to CP for easy demonstration and for study. Right, now what happens if I pitch up more?
The point will move.
So
furthermore.
what is happening here,
Forward.
when you increase the angle of attack, it's correct that because of the camber and because of the increase in angle of attack, what happens to lift? Lift is, what is the equation for lift? CL Q S. So we are changing the configuration of the wing, therefore the wing area is still the same. Even though the wing area is kind of reducing here, we're not considering it at the moment. You can see what happens. The CL depends upon angle of attack as well as camber. You keep increasing the angle of attack. For example, I'm taking this is a non-symmetrical or kind of a cambered wing, and therefore, if this is the angle of attack alpha and CL, we have seen this graph before. For a wing that is cambered, what happens at zero angle of attack? You will still have some value of lift production because of cambering, and then if you want a zero lift coefficient, you have to go to negative angles of attack. And what happens when you increase the angle of attack? The coefficient of lift keeps on increasing, and does it infinitely increase?
No, sir. It is the maximum.
That's right. So you see what happens is when you keep increasing your angle of attack, this separation point and transition point keeps moving towards the leading edge, and you will reach a point where this transition and separation, transition point or the separation point is kind of exactly here. It reaches here as you keep increasing the angle of attack. Now, the entire top surface of the wing is not producing lift. There is a reversal in pressure gradient. We have seen an elaborate diagram of this in one of the previous classes with all the different positions drawn. And at that point, what happens? Your lift reduces gradually, not gradually, probably immediately, but it is not like a fall, but the lift reduces with any further increase in angle of attack. Right? What is this angle of attack called? Alpha stop, or it's also called as the critical angle of attack. Generally, for a modern jet, it's about 15 to 18 degrees, and the corresponding value of coefficient of lift is called as
6 degrees.
CL max.
Right?
4 degrees is not. 4 degrees is the optimum angle of attack, where you have the maximum lift, best lift bar drag ratio, where you have maximum lift.
Alpha stop we have 16 degrees.
Yeah, 16 degrees. Yeah. So generally 16 is a fixed value, so it's generally between 15 to 18. Yeah, 16 to 18. That's fine. Now some textbooks you can see 14 to 18. So it's in that range. Average you can take it as 16.
Okay.
You understand the problem here? If you keep increasing your angle of attack, that is one maneuver which is going to shift these points towards the leading edge, which is not a favorable case, because you will all of a sudden lose the lift once the pressure gradient reverses. Pressure gradient reverses means low pressure, which is supposed to be above the wing, now becomes under the wing or probably in front of the wing, and that is a reversal of pressure gradient. Is that clear?
So you mean to say it will generate lift in the stagnation point maximum.
No. Yes, correct.
When transition, when transition point reaches the stagnation point.
Yes.
Maximum lift.
Yes. And after that, that moves towards underneath the wing. It's now going to produce the force in the opposite direction. It is still producing the force, but in the opposite direction, that is negative to the lift. So it's kind of now in the direction of the weight, and therefore the aircraft loses the lift. Is it clear, all of you?
Okay.
Transition point and separation point. Right?
Okay.
Yes. So let's look at this question here. Yes, Anuj, you can answer that question.
Okay.
Question number 121.
121.
Which of the following statements on transition point is not correct? Affected by surface conditions, irregularities will increase skin friction drag. Now remember, another problem with this transition point is if this particular area is not smooth, and tell me some of the reasons why an aerofoil or a wing would not be smooth.
Because of icing or
Icing, yes, dust, all these things can actually cause the flow to be turbulent much before this normal transition point. Therefore, transition point practically shifts more towards the leading edge. Yes, that's correct. It is affected by surface conditions. Irregularities will increase skin friction drag. That's the drag associated with it is a skin friction drag because of the friction with the skin, because of ice and stuffs. Yes. B. Affected by adverse pressure gradient.
Yes.
Yeah, it is affected by the adverse pressure gradient. Say again.
What's the question number again?
121.
121.
121.
Okay, copy.
Yeah. So 121 option Bravo, affected by adverse pressure gradient. Yes, that is why the transition point exists in the first place. So after transition point, you have an adverse or reverse pressure gradient, where you have air now moving from a lower pressure to a higher pressure, that is against the normal gradient, right? What happens to what is TP? TP is at or near the point of maximum thickness.
Yes.
Correct? Now it is more appropriately, it is at or near the point where the area of cross section is the least. And for a normal configuration, that is usually along the point of maximum thickness. Do you see here? Here the point of maximum thickness is somewhere here. But the lowest area of cross section is here.
Okay.
Normal configuration may, yes, point of the point of lowest area of cross section and the point of maximum thickness can be the same. Right? So what about delta? Flow becomes laminar from turbulent.
That is correct.
So also wrong because it's turbulent flow
No,
from
it becomes turbulent from laminar.
It becomes laminar to turbulent or turbulent from laminar.